Hi, welcome back everybody. In our last example, we talked about how we had two helmsmen on a ship that were trying to turn the wheel two different ways and apply two different torques. And we actually jumped to a concept, which is what we're going to touch on in this segment right here, which is the idea of net torque. I kind of jumped the gun right on that, but I think you probably saw that coming. You recall that in previous chapters where we had the net force, of course, the sigma, meaning the sum of all the forces, equals mass times acceleration. Well, the corollary to rotational forces is very, very similar. This is our rotational force, torque, right? Tau is the symbol. And we saw that in that last example, we saw that the net torque was torque 1 plus torque 2 plus, if there was more torques, torque 3, etc., so on and so forth. But just like with dealing with forces, the net force is the sum of all the forces, but it's also described as mass times acceleration. With rotational dynamics, the net torque, torque 1 plus torque 2 plus torque 3, etc., is going to be equal to our moment of inertia, which is our corollary to mass, times our angular acceleration, which is our rotational corollary to linear acceleration. All right, so this is very, very parallel to what we learned about in forces. Net torque is I times alpha, in the same way that net force is mass times acceleration. All right, so mass linearly speaking, is moment of inertia. Linear acceleration is alpha, angular acceleration, and of course, force becomes tau, our symbol for torque, rotational or angular force. Okay? So let's apply this in yet another example. Now, this example might drive some of you crazy because if you look, you'll notice that it's all general terms. But that's okay because this is going to be good practice for applying a rotational kinematics and dynamics with applying that and comparing that to linear dynamics and kinematics, which I know you guys probably already have a handle on. Okay, so we're going to read through this. And we're going to write down what we know or what we supposedly know, and then they're going to solve for these three different parts right here. Okay, so we've got a fisherman dozing, and the fish takes off on the end of the line. Okay, so the fish applies this tension force from the edge, we might say tangentially from the edge of the reel, and takes off. So this is a force right here. That T, what I'm going to do is I'm going to call that F sub T, force of tension. All right, and the reason for that is because time is going to be in here. We're going to be dealing with time later on, a small t, and I don't want to get our t's to get mixed up. All right, we want to remember that this tension really is a force right here. So I'm going to call it F sub T. Okay, so the fish is pulling with that force of tension. Poorly drawn F. Let's try that again. F sub T. Okay? We got that. So the tension force is something. It's initially at rest. All right. So our initial angular speed is 0. We know that for sure. Rotates frictionlessly. That's good because we don't want to deal with friction, at least not quite just yet. And it pulls the fish pulls for time t. So time is something that we know, even though we're just going to use the general term t for time. Radius, r, okay, radius of the spool, we're going to use a capital R right here. That's going to be something. Moment of inertia is something. And what we want to find is these three values right here. We want to find the angular displacement of the spool. Okay, so delta theta, how many revolutions, or actually we're going to say in radians, how many radians worth of pulling just got pulled out right there as the fish ran with the line right here. B, we want to find the linear, or the length of line pulled from the spool during this time. So that's going to be very closely related to our angular displacement, but we're just going to call that delta x. We want to solve for. And part C, we want to find the final angular speed of the spool when the fisherman finally realizes it and grabs onto the spool after time t. Okay, so with these things all laid out, I'm going to shrink all this down so we have a little bit more space. Okay, let's put this up there like so. Okay, so part A, we want to find the angular displacement. All right, so delta theta right here. This is all going to be in general terms. All right, but we want to find out what the angular displacement delta theta is in terms of all these other values that we have right here. Okay, so we've been talking about force applied at a radius, and of course that's going to be torque. But we've also stated that torque or net torque is I. Net torque is our moment of inertia times the angular acceleration. All right. Well, if you recall from previous chapters dealing with forces, things like displacement and velocity, what were they tied in with? When they were tied in, those kinematic values were tied in with acceleration, just like those rotational kinematic values are tied in with rotational acceleration as well. So we're going to find that our link to values like velocity and displacement of time are going to be wrapped up in here. Our I probably isn't going to change. In fact, the I is very much like mass, just like in our forces chapter, mass didn't change. But the acceleration was a function of all those other kinematic values. And of course, we know what net torque is described as right here. So we can say, let's go ahead and just start by stating that net torque, all right, is our moment of inertia times the angular acceleration. And let's make another statement about net torque. Net torque is really the force applied at that radius, right? Well, what's the force that's being applied? Well, it's, actually I'm going to put radius first. Radius times the force. What is that force? It's that force of tension that the fish is pulling with, right? R times F sub T. That's going to be our net torque, which is going to be equal to our I times, all right, let's make a statement now for acceleration. In fact, I'm going to write it. I'm going to write down at the bottom right here, so we kind of stay out of the way up here. If we're trying to find our delta theta, our change in angular displacement, and we want that in terms of acceleration, and we have time right here, which one of our kinematic equations best relates them all together? If you look at all of our kinematic, now you could either use linear kinematics or go right to our rotational kinematics. It's all the same equations, just with different symbols. You'll recall we have an equation like this. Delta theta equals initial angular velocity times time plus 1/2 angular speed times time squared. Does that look familiar? All right. So if our initial angular speed is 0, that just drops out, and we have our acceleration in terms of things like time and in terms of our angular displacement. So let's turn around and solve this for acceleration and stick it right in there, okay? So our acceleration is going to be, what do we do? I'm going to multiply up my 2, all right, 2 times delta theta. I'm going to divide down my t squared, right? Excellent. So if acceleration, now I'm going to put it back up here, is 2 delta theta over t squared, then I'm going to stick that in for that. So that's really what's going to go right in here next to my I. 2 delta theta over t squared. All right, remember, that's our link. Acceleration is our link to things like initial velocity, final velocity, displacement, time, etc. Okay? That goes right in there, and it's substituted in there for that. Okay, now we actually have our delta theta in terms of all the other things that we're given. Our time, our moment of inertia, our force, and our radius. Let's just turn around and solve for that displacement right there. All right, so if we solve for that angular displacement, what's going to happen here? Well, time is going to get multiplied up, or time squared, I should say. It's going to get multiplied up, and our moment of inertia is going to get divided down. So it'll look like this. Radius times that tension force, which of course is the torque, times t squared divided by our moment of inertia. So again, this guy comes down, and this guy gets multiplied up, is going to equal our change in angular displacement. All right, and that's our final answer for part A. We don't have any actual values. We're just using general terms, but that's going to be our answer, solving for the angular displacement, delta theta, of the spool that has this moment of inertia. It's given this amount of time, and it's experiencing this force that applied at that radius. All right. Well, part B is asking us what is the linear component of this, or what is the linear displacement that the string or the line has experienced. All right. Well, you probably recall from the beginning of last chapter that linear displacement, delta x, equals radius times angular displacement. Wow, this is easy. So all we have to do is multiply this by radius, by r. And you know what? I wrote a lowercase r, but in this problem it's been an uppercase r. That radius times all this right there. Well, we'll just substitute that in for our angular displacement. We have a statement for our linear displacement. Delta x equals, so it's r times r, force of tension, times t squared. So this r winds up getting squared, right? So r squared times a tension force times a time squared, all divided by our moment of inertia. And that's it. That's going to be our answer for our linear displacement, because linear displacement is related to angular displacement simply by virtue of the radius. All right, lastly, we want to solve for, and I hope I have enough space. If not, I'll just make some more. Part C, we want our final angular velocity, our omega final. Okay? Well, we know some things like time. All right, we know some things like angular displacement and so forth. We also happen to know, well, a couple different equations that can describe our angular acceleration as well. Since we know time initially, and since we know our angular displacement initially, I'm going to stick with those values and see if we can come up with an equation that talks about our final velocity in terms of those two. Final angular velocity, angular acceleration, time. Do we have an equation for that? I think we do. You might recall this one right here. Final angular speed equals initial angular speed plus acceleration angular times time. Of course, if the initial angular speed is 0, that goes away. Okay. And so we have our final angular speed is the acceleration times time. All right. What I'm going to do is, well, we can actually do this a couple different ways. I'm going to do it like this. There's a couple different substitutions that we could do. Let's write this in terms of acceleration. Okay. Acceleration, we're going to divide down the t. Of course, the omega initial goes away. Acceleration is going to be simply our final angular velocity divided by time, right? Now let's go back to our most basic statement about net torque that we've been talking about. We can say that the net torque equals I times our angular acceleration, right? And of course, net torque is radius times tension force equals I times our acceleration. And since acceleration is final angular velocity over time, then we can say that the radius times the tension force, that's our net torque, equals I times final angular speed over time. All right, now these are all values that we are given at the outset. Our moment of inertia, our force, and our radius right here. So again, I like describing a value in terms of values that were already given. All right, all these were told at the very outset. The only thing remaining to do is to rearrange these and solve for our final angular speed. All right, so we're going to multiply up the time up here, and we're going to divide down the I, moment of inertia, and we'll have a statement about our final angular speed. So final angular speed is going to be radius times tension force times time. Imagine how confusing that would be if we left that with a capital T right there. R times capital T times lowercase t. So that's just our force right there. Divided by what? Divided by our moment of inertia. And that's going to be it. All right, it may not look like a whole lot right now, but these were all values that we were given at the outset of the problem, and that we can plug in to solve for our final velocity. All right, so we solve for our final angular displacement, our final linear displacement, really as a function of that, and our final velocity using net torque equals moment of inertia times angular acceleration that we have stated for this part of the chapter. All right, example 11.2. Thanks for following along. Make sure if you have any questions, you ask me, and I'll see you on the next one.